Today we're going to take a look at vector and parametric equations of a line in 2 dimensions. So the first thing that we have to think about is a direction vector. So what is a direction vector? A direction vector is a non-zero vector. We use m to represent that direction vector, and you'll see why in just a little bit. It's represented by a vector coordinate AB, and it's going to be parallel to a given line. So when I say parallel, it could actually be parallel. It could be on the line. It could be going in the opposite direction to the line. It's a scalar multiple of that vector on a line, but it's going to have a tail at the origin 0, 0, and its head at the point AB. So the x and the y coordinates of the direction vector are called the direction numbers. And we use the vector m because it's like the slope of a line. So back in grade 9, when you started to learn about equations of lines, we learned about y equals mx plus b. And when we learned about y equals mx plus b, we said that b is the y-intercept and m is the slope. So when we think about vector equations of a line, we want to think about the direction vector as our slope of the line. And instead of always having to use a y-intercept, we can use any point on that line. So what does the direction vector tell us? Well, if we have a line that passes through the point P, which has the coordinates 1, 3, and it has also a direction vector m, which is equal to -3, 2, we can think about drawing in our rise over our run. So in this case, we would have a rise of 2 and a run of 3. So if I was thinking about recreating this, and in this case, our rise would be negative because it's really going down from left to right if we want to think about that. If I was going to recreate that at our point P, I would go down 2 over 3, and this would be my next point right there. And that would be the same vector as that red one there. And we can see, because both of those vectors are parallel to each other, they have the same magnitude and the same direction. In this case are equal, but we can also think about applying that sort of direction vector like a slope to come up with more points on that line. So I could go over 3 and then up 2, and there's another point on that line. So I can extend this line all the way up there. I could extend this line going all the ways towards the right. So that's how we can use that direction vector like a slope to inform us about what our vector equation looks like graphically in 2 dimensions. So how can you draw the direction vector? Well, you can determine direction vector from any line. Again, we want to think about sort of a slope. If you were trying to find slope of a line back in grade 9, we would pick 2 points. We would pick a point that had nice whole numbers as our coordinates, and then we would pick another point on that line. In this case, I'm going to choose the point up here on the right hand side. So if I was looking for the rise and the run, again, I could say, hey, this is going to go up 1. This is going to go over 4. 1, 2, 3, 4. And so if I wanted to determine a direction vector starting from the origin, I would go up 1 and over 4. This would be my direction vector that starts from the origin and ends at a point. Okay, and again, this is what we call vector m, and I can say vector m has a x coordinate or an x component of 4 and a y component of 1. So again, just to recap, in grade 9, we thought about slope, rise over run. So we're still going to think about that when we look at some examples today, but that rise in this case would be considered our B, so the y component. Our run would be considered our A, okay? So I mentioned that we need to think about using any point on our line. So if we want to consider ourselves moving along a straight line, and we can put ourselves anywhere on that straight line. So we could put ourselves right here at the top of that straight line. And we want to move along that straight line. Okay, so we would have a starting point. This starting point would be like our point on a line. So in this case, it's going to be A that we're going to reference. So A is a point on the line. It could be a y-intercept, but it doesn't have to be. And so if I wanted to represent my position by using P, so this is my position at any point on that line. So we're going to just recognize this as an arbitrary xy. You'll notice that our starting value for A, we used x0 and y0. This is like that sort of initial value, our starting point, okay? So that's the notation that we use for that. And then if we wanted to say, hey, eventually I might get to B, maybe, right? Just depends on how far I go along that line. So how could we represent our position on there? Well, we could represent that horizontal position. So that would be helpful for us to think about. So that horizontal position on the from point P compared to our original starting value. So if I wanted to think again about rise over run or slope, I would find the difference between the x values, the difference between the y values, and then use that to sort of think about my position. Okay. So if I wanted to think about my position for x and I wanted to figure out my run, so I would take my point that I'm going to end up at, so my arbitrary x value, and I would subtract my initial starting point, so my x0. So if I wanted to represent my position in relation to my horizontal position, I would say that somewhere along this vector, if I'm just looking at the x component, and I want to think about, maybe you want to think about function notation a little bit, where we would think about v at t. I'm not going to put my t in brackets. This would be like I was multiplying. Well, this position here, I could find it by doing that difference. Okay, so I could do the same thing with my vertical position. So I want to end up at y, but I started out at y0. And that would give us my vertical position somewhere along that line or somewhere along that vector in terms of maybe a velocity. And then I would say, okay, that's going to be multiplied by that random t because I don't know what my time is. So I don't know how far I'm traveling in a certain distance. And that's going to be y minus y0. So our vector v is represented now by this arbitrary vx, vy. I'm not quite sure what those values are. T is going to be the time traveling from A to P. So if we wanted to think about these equations, this t is just a random parameter. It's a random variable that represents your position in any given time. In this case, it's representing the relationship between x and y in terms of time along that line. We can use this concept of the x minus x0 to come up with a parametric equation of a line in a plane, okay? So that's really important now. So we're taking what we knew about y equals mx plus b, and now we're going to represent it using vectors and vector terminology now. So my value for x can be found by looking at my initial value of x or the coordinate of any particular point on that line. So again, maybe when we thought about y equals mx plus b, this point on the line was our b value. It was our y-intercept, but it doesn't have to be. Okay, so this is just any particular point. So if you wanted to think about that, any particular point, sort of relating to our y-intercept, you can, but again, it doesn't have to be necessarily a y-intercept. So x and y is just the position of any point on the line, so it's our random x and y there. Okay, so that's important, right? When we found the equation of a straight line, the y and the x gave us the value of any point along that line. And our AB is a direction vector, which we're going to represent maybe as our vector m, but this direction vector relates down back to our slope. So the slope of the line, and because we have just a random t to represent a time on the line or a position on the line, we're going to think about that in terms of that just a random variable to represent that distance. So let's take a look at some examples where we're sort of going to take what we know about equations of lines in 2 dimensions and apply it now to this parametric equation of the line. So first, let's talk about direction vectors. So again, I talked about direction vectors being similar to the idea of slope. So if I have a line with a slope -7/9, how could I represent this as a direction vector? Now, when I think about slope, most of the time I think about the negative value being with my rise because I'm going either up or down. In this case, I would go down. So I could apply that negative to the numerator, or operations with fractions and negatives tells us that I could also throw that in the denominator. So you might come up with a direction vector that might be slightly different than the person beside you if you have a negative slope, because you might put your negative value in the numerator versus the denominator. You're still going to get a similar direction vector, just one is going to be a scalar multiple of the other if I multiply it by -1. So my direction vector says I'm taking my rise, right? So this is the y component or the b value when we think about our direction vector m. So direction vector m is a, b, where a is that x component, b is the y component. So the rise is considered our b and the run is considered our a. So if I wanted to represent this first slope, -7/9, as a direction vector, I would represent it as my run would be 9, or my a value is 9, and my rise is -7. If I put my negative in the denominator, my direction vector would be -9 this time, and then +7. So these vectors are just scalar multiples of each other. And because they're scalar multiples of each other, they essentially represent that same vector, right? Just one is going to be pointing in a slightly different direction from left to right, but it's still going to be fine, okay? So now let's take a look at this next one. So a line that passes through points A, 610, and B, 216. Again, think slope, right? Slope is rise over run. And I find rise by taking the difference of my y coordinates, in this case 16 minus 10. And I would take the difference between my x coordinates, so 2 minus 6, and that would give me 6 over -4, which simplifies to 3 over -2. Now again, it doesn't matter where you put that negative. I'm going to keep it in the denominator because that's where it was when I did my calculations. So if I wanted to represent my direction vector m, I would say it's going to be -2, 3. If I wanted to think about a horizontal line passing through 3, 2, I want to really think about what a horizontal line is. So a horizontal line has a slope of 0. So if I taught you in grade 9, you might have remembered Mr. Slopeman, right? So we looked at, what is the slope of the different types of lines. A positive line goes up from left to right, a negative slope goes down from left to right. A vertical line has a slope that's undefined, and a horizontal line has a slope of 0. Because it has a slope of 0, and we want to think about rise over run, we're thinking it has no rise, so that's our 0, but I could have a run, right? So my run could be any value in this case, so we're just going to give it a value of 1. it's important for us to think about that because it allows us to have a direction vector now with an A value and a B value. This is our B, that's our A. So if I was thinking about my direction vector, it would be 1, 0. That's a direction vector that is along the horizontal line. You'll also notice that, hey, this is also our unit vector along the x-axis, which sort of makes sense as well. Now, perpendicular lines. Perpendicular line, if we want to find a line perpendicular to y equals 3x plus 5, again, we want to think about what would that original slope have been in that original line. Well, my original slope would have been 3, or 3 over 1 if I wanted to think about that as a fraction. Perpendicular lines have slopes that are negative reciprocals of each other. So I'm going to flip my fraction, but change the sign. Again, it doesn't matter where you put that negative sign. Okay, so now this allows me to find my direction vector of a line perpendicular to y equals 3x plus 5 would be 3 and then negative 1. So really think slope, rise over run when we're thinking about direction vectors. We can also take a look at finding our direction vectors or even equations by looking at 2 points, okay? So if we were trying to find a line that passed through the point C, which was negative 4, 6, and D, 1, negative 5, could we determine the direction vector CD? We could think about this again in terms of slope, right? That's one way to think about this. So the difference between the y coordinates over the difference between our x coordinates, rise over run. So we could have negative 5, take away 6, and then 1, take away negative 4. That gives us our negative 11 over 5. Okay, from there we could find the direction vector. So our run is at the bottom, so that's our x, and then our rise is on the top, that's our negative 11. We could have also thought about this as, hey, if I want to find a vector between the points C and D, right, then I am just taking my x coordinates, subtracting those, so y minus 4, and my y coordinates, negative 5, take away 6, and that will also give me 5, negative 11. So 2 ways that you could think about direction vectors if you're given the coordinates of that. We could have also done that just finding the vector between 2 points when we looked at the equation, so a line passing through points A and B from the first side of the page. So once we found the direction vector, now we can start to think about the parametric equations. So the parametric equations of a line talks about representing the x coordinates and the y part, so the x component and the y component. So the x component comes from our x0 plus an arbitrary value times our run. And then the y component is the initial value of our y plus an arbitrary value we're going to call t times the rise component of our direction vector. We often put these in a set of curly brackets to show that they are connected, and this would be the parametric equations for the line. This is like our basic y equals mx plus b, but for parametric equations. So if I wanted to represent the parametric equations for my line now, or my vector that goes through CD, then I would take a look and represent this as x equals. Now, I can either choose to use point C or point D as my initial point. I'm just going to go ahead and use C, alphabetical order. So my initial x part of C is negative 4. My A value, right, comes from my direction vector, that's 5. And my t is my random variable. For my y, I'm going to use my 6 because that's the y component of C, plus my rise, in this case it's a negative 11, so I'm going to go ahead and change that to negative 11, and then my random variable t. So this would be the parametric equation of a vector, or line represented by a vector. So if we know the parametric equation of a line using vector sort of notation, then we can answer some questions about that. So the next question says, hey, what is that point on the line that corresponds to the time, or the t, or the variable being -2? So I'm going to look at my x component and my y component. So my x, I can find x by taking -4 plus 5, but instead of putting t now, I'm going to put -2 in its place. So if I just simplify that using order of operations, I get -14. I can do the same thing with my y. My y in this case is going to be 6 minus 11 times -2, which gives me 6 plus 22, and that gives me a value of 28. So therefore, the point when t equals -2 is going to be -14 and 28. So this is a point on that vector line when our t value is -2. We can also use our parametric equations to determine whether a point lies on that line, okay? So the first thing we might want to do is we might want to think about, well, let's take a look at our x coordinate first of all. So the parametric equation of my line for x was -4 plus 5 times t, okay? But my x value is going to be 6. So I'm going to have 6 is equal to -4 plus 5t. So I'm going to isolate for t now. So if my point lies on the line, then the value that I get for t when I use x should be the same value as what I get when I solve for y. So I'm going to have, bring the -4 over, that gives me 10. So 10 is equal to 5t, divide both sides by 5, I get t is equal to 2. There's a few different ways that we can think about finding out whether the y component is going to be -1. We could just do the same thing with our y values, right? We could plug in, we could do 6 minus 11t, right? We could plug in -1 here, and we could isolate for t again, just like we did for x, right? So we would get -1 minus 6 is -7. That's equal to -11 over t. And then if I go ahead and divide that out, I get t is equal to 7 over 11 when I think about the negative signs. Because the t's are not the same, the point doesn't lie on the line. Okay, so in order for the point to be on the line, our t value for the x component and the y component has to be the same value. Another way that we could have done this is we could have also said, okay, well, if my t value is 2, and that's what I solved for when I put 6 in for my x, I can sort of do a check for the y. So my y value, if I plug 2 in there, should give me -1, right? And I can see when I do that quick calculation that it doesn't give me -1, right? -16 is not -1. So it's another way to show that it doesn't lie on the line. So I can say with confidence now that therefore, because I showed it in 2 different ways, therefore the point 6, -1 doesn't lie on the line. If we wanted to take our parametric equation and then put it back into slope-intercept form, just like I would have come up with my equation of a line in grade 9, I can go ahead and do that. So I came up with my parametric equation. So my parametric equation, just to recap, was x equals -4 plus 5t, and y is equal to 6 minus 11t. That's my parametric equation. we're going to see lots of different variations to write the equation of a line using sort of vector notations, just like we would have seen a few different ways to represent an equation of a line in grade 9. So we looked at slope-intercept form, we looked at standard form, and when we thought about parabolas, right, we had multiple ways to represent the equation of a parabola. So know that even though I'm going to come up with different notations, they still represent that same line or that same vector on that plane. So this was the parametric form, or the parametric equation. So what can I do to now put this into slope-intercept form, which is y equals mx plus b? Well, from my parametric equation, I can say that my direction vector was 5, negative 11. And what that means in terms of y equals mx plus b, my slope was negative 11 over 5. Okay? So if I know that my slope was negative 11 over 5, then I can also think about, well, what is a point that I used in my parametric equation? So the point that I used, so my initial point that I used, so I'm going to call that P0, was negative 4 and 6, okay? Now, I can use this was point C, right? So this was C. I could also use point D, okay, as my value. So I could have used D in here as my equation for my parametric equation. It would have been the same thing. So when I'm looking at my equation in y equals mx plus b form, when I'm trying to find my b value, I can either substitute the x and y in from D or C. It doesn't quite matter. I'm going to choose to use D right now because D has smaller numbers. I have a 1 in there for my x, which, you know, I like, right? I'm not going to have super messy fractions. I'm still going to have fractions, but not super messy ones. So I'm going to sub this in for my x and y. So I'm going to have negative 5 is equal to negative 11 over 5 times 1 plus b. So I'm going to solve for my y-intercept now. Okay, so I can write negative 5 as negative 5 over 1. Negative 11 over 5 times 1 is just negative 11 over 5. So I'm going to bring this to our left-hand side to give us positive 11 over 5. Okay, and that's equal to b. I can also say, hey, this negative 5 over 1, I can write this with a denominator of 5 by writing this as negative 25 over 5. And so my b value is going to be negative 14 over 5 when I add those fractions together. So I have my slope, I have my y-intercept. So the equation of my line in slope-intercept form is y equals negative 11 over 5 x minus 14 over 5. So we can take this new learning and apply it, or dumb it down, if you want to say, back into what we would have learned in grade 9. Okay, so different representations. Can we use y equals mx plus b in 3 dimensions? No. Okay, we can only relate this back to 2 dimensions. Okay. All right, so again, I'm going to talk about some different representations of vector equations of a line in a plane. Okay, so any point on the line can be found using our parametric equations. We saw that earlier. X equals x0 plus at, y equals y0 plus bt. Okay, so we can say that any point on that line now, so p, x, y, can be represented by the x component, so x0 plus at. Right, this is where it comes from. So this part is right there, and our y value is right there. Okay, so we can now say that if I started at the origin and I go to that point P, what if I represent that by just a single vector now that we're going to call r? Okay, so when I'm writing the vector equation of a line, I'm always going to start with r, vector r equals. It's just a notation that we're going to use. So I can take what I knew or what I learned about vector addition and breaking that all up in our properties there to now split this up so that it was x0, y0 plus at plus bt. Okay, so I can break this up into those two sort of vector components if I wanted to think about that, or the coordinate components. And then I can take my scalar multiple t and bring that out of my AB. And then that AB was our direction vector. So it sort of comes, I can take what I knew about parametric equations and now sort of translate that back into what we call a vector equation of a line. Okay. So let's work with this vector equation of a line now. Okay, so we're looking at vector r is equal to our initial point. So again, this is any point on the line plus a scalar. We don't know what that is, right? That's our unknown times the direction vector. So if I wanted to find the vector equation of the line that passes through the point -7, 8 and is parallel to the y-axis. So the y-axis is vertical, right? This is a vertical line. Again, if I think back to Mr. Slope Man, the slope of a vertical line is undefined. Okay. So what would that have meant? Well, slope is rise over run. Okay. So rise over run means, and for a vertical line, remember this is a vertical line that I'm thinking about. My rise, I can go up or down anytime, right? Any height, doesn't matter. So my rise would have a value, right? So that's going to be 1. But my run, I'm not going left to right at all. So my run would have been 0. And that's where I get that sort of undefined from my slope, okay? So because I looked at that, if I was to come up with my direction vector, I can use the sort of rise over run now. So my run being 0, my rise being 1, and you'll notice that this is the unit vector along the y-axis, which makes sense because it's parallel to the y-axis. So if this is my direction vector, I'm going to use my point. This is going to be my point P now. So I'm going to put those pieces together. So vector R can be represented by -7, 8 plus a random variable t. I know it gets confusing when we have a plus and a t, and then 0, 1. If it's really confusing to have this as t, you are welcome to use another variable here if you want to, okay? So that's our vector equation for this equation there, or that scenario. What if I have a line now that has a slope of 0 and passes through the origin? We already saw in a previous question that if I have a slope of 0, this is going to be a horizontal line, and a direction vector for a horizontal line would be 1, 0. So it's just our unit vector along the x-axis. Okay. And if it passes through the origin, that's going to be the point 0, 0. So if I put those pieces together, vector r is represented by 0, 0 plus a random variable t times my direction vector of 1, 0. What if I wanted to now write an equation for a line that has a slope of -3/4 and passes through the point 1, -2? So -3/4, I can put that negative in the numerator or the denominator. Doesn't quite matter. I'm going to go ahead and throw it in the numerator. Okay, so my slope is -3/4, which means my direction vector is for -3. If I put the negative in the denominator, my direction vector would be -4, 3. Okay? Doesn't matter, they're scalar multiples of each other. My point is 1, -2. And so I'm going to put those pieces together. My vector equation is r, 1, negative 2, plus a random variable t times my direction vector for negative 3. And last example, can we find a vector equation that passes through negative 7, 8 and is perpendicular to the direction vector m, which is negative 3, 2. If you want to go back and think about what would this have been in terms of rise over run, my original slope here, right, would have been my rise is 2, my run was negative 3. If I want to think about what's that perpendicular slope, it would have been 3 over 2. So flipping that fraction, changing the sign, which means my new direction vector will now be 2, 3. Okay? And my point is negative 7, 8. Putting those pieces together, I get r is equal to negative 7, 8 plus a random variable t times my direction vector, which is 2, 3. So this is the vector equation. If I want to put a vector equation back into parametric form, I can do that. So I can now just represent the x component. So my x value is going to be negative 7 plus 2t. My y's is 8 plus 3t. Okay, so this is the parametric equation of a line. So you'll see how those are connected. Okay. If I have equations in parametric form, another type of equation that you might see, or another representation, would be a symmetric equation of a line. And that's when we isolate for t. So if we take the x component, and in this case, if I was looking at negative 7 plus 2t and 8 plus 3t, I would go ahead and isolate for the t for my x component. So I would get x plus 7 is equal to 2t. So t is equal to x plus 7 divided by 2. So this is where it sort of comes from in terms of that t equals x minus x0 over a. Okay, so that's that for that. I can do the same thing with my y component. I'm going to isolate for t. So it would be y minus 8 is equal to 3t, or y minus 8 over 3 is equal to t. And then the symmetric equation says if these are both equal to t, well then my x part of this should equal my y part of that. And so the symmetric equation connects those two parts together. So then I would say x plus 7 over 2 is equal to y minus 8 over 3. When we do some more calculations with equations of lines in planes, we are going to see how this all works. But for now, if you can write an equation in parametric form or vector form, you're good to go for right now. Okay? So now I want you to try some questions from 8.1. So those questions 1 to 14 is sufficient. There is a mistake in 10b, so make sure you make note of that. All of this is in the OneNote, and it's in the package that you're going to get when you do these questions. If you have any questions as you're going through this, please feel free to send me an email. Otherwise, I will see you when I return.